you can see my screen for now. Okay, so here's the questions, the two questions for the quiz yesterday. Those will introduce some basic concepts that we learned in the leveling and the angle measurement. So the first question want us to list the size which we are taking on at a turning point, where we will usually for the direct differential leveling or direct leveling, we'll only consider two sides, the foreside and backside. So the answer here should be C, which will be the foreside and backside. And for the second question, which will be related to the conversion between the azimuth and the bearing, the one wants us to find out the bearing at the azimuth from the south pole of the line A to B. So here you need to pay attention about the setting. The south pole is not the default azimuth, which is from the north pole. So what we do is like, let's first draw the line AB with respect to the north and east, south and west direction. So the bearing of the line A to B is a north 89 degree 30 minutes. So we should know that this line falls in the region to the northwest region, and the direction should be something like this one, A to B, and this is the bearing 89 degree 30 minutes. But the problem wants us to find out the azimuth from the south pole. So with that, we will always start from the south direction and then find out the clockwise angle from the south pole to the angle, to the direction. So with that, you can find out the azimuth from the south pole of the line A to B. That will be 180 degree minus 89 degree 30 minutes, which will give you the answer as 90 degree. Sorry, just disappeared. So let me just quickly draw that one again. So from A to B, north and south, we have the bearing 89 degree 30 minutes, and the azimuth will be from the south pole will be 180 degree minus 89 degree 30 minutes, which will give you the answer as 90 degree 30 minutes. So that will be this value. So if you choose this one, that means that you get the right answer. So that will be the answer of the quiz. Do you have any questions about it? If no, then I'm gonna start the lecture today. Okay, let me just exit this one. And try to open the lecture where we left. So in the lecture yesterday, we have stopped at the part about introducing the measurement of the horizontal angle with repetition. So what we said that we will try to measure one angle multiple times to minimize the impact of the system errors or the human mistakes. With the multiple time, with the repeated measurement, we are able to make sure that the average value from the repeated observation will be close to the true angle that we are trying to measure. So there will be some steps to conduct the repetition. We're gonna first measure the angle from A to B and reverse the telescope and measure A to B again, and repeat this one for a lot of times. And basically for the measurement, the angle measurement with repetition, we will have the recording like this table. So in the usually it will only have three recordings. The first one is the first direct reading, which is the initial angle that you measured, you read from the instrument. And you will also have the first direct reading, which would be the angle, you reach when you move the your telescope from 0 to A to 0B. And with that, you can find out the first initial value of the angle between OA and OB. And then you will have some reverse reading. So you repeat this one for 6 times, and then you have another final reading. So with that, I will then show you how to calculate the how to use this reading to find out the average value of the angle AOB, and how we can improve the accuracy of this measurement. So you can actually find out the range or the approximate value from the 2 direct readings. So the reading 1 represents the direction of OA, and the first direct reading represents the direction of OB. So you can find out the angle, find out the approximate value of the angle AOB, say that alpha equal to, say this one is alpha 1, alpha 0, this is alpha 1. So that would be approximately alpha 1 minus alpha 0. And you can, in this case, you can find out the answer as minus 136 degree, 1 minute and 50 seconds. So you can find out the approximate value as 80 degree, 19 minutes and 10 seconds. So this is the we should say that this is the approximate value of AOB. It's not a 100% accurate, but we should know that the angle AOB should be around some value of this one that we conduct from the direct measurement. And then we conduct 6 reverse. So n equal to so we have n equal to 6. So we do this. This indicates that we do the measurement of the angle A to B for 6 times, and then it indicates that for this for the 6th time measurement, the total angle that we measured will be approximately n times alpha. So that will be 6 times 80 degree, 19 minutes, 10 seconds. So again, this is still the approximate value, and you can see that the value is the total value is 481 degree, 51 minutes, 55 minutes, 0 seconds, and this one is actually higher than 360 degree. So it means that this angle, this measurement must pass the 360 degree, pass 360 degree or 0 degree once, because for most of the instruments, they can only measure the angle from 0 degree to 360 degree. If the cumulative angle is higher than 360 degree, then it will go back to 0 degree and repeat it again. Depending on the number of the reverse that you applied, this value could be more than 1 360 degree, could be higher than 2 360 degree. So you have to identify how many times you pass the 0 degree or 360 degree of the instrument. For this specific example, it only passed once, so we get a k equal to 1. And then we can estimate the average value of the angle A to B. So the average value, which is the value we will estimate from the repetition, will be the we define this one as alpha 6 this will be alpha 6 plus k times 360 degree, depending on how many times you pass through the 0 degree or 360 degree, minus alpha 0 divided by the number of the reverse. So in this case, we get the value as 257 degree, 57 minutes, 50 seconds, plus 1 times 360 degree minus 160 36 degree, 1 minute 50 seconds divided by 6. So with that, you can actually find out the value, the average value from the repetition as 80 degree, 19 minutes, 20 seconds. So clearly you can see that this value is a little bit different from the one with only one direct measurement. But we will assume that the one from the repetition will be more accurate, because you repeat this one a lot, you can try to eliminate the potential errors from the human operators and from the systems. So that's the reason for us to introduce the repetition for the angle measurement. And the most important part for this measurement, and also this is the very common error when you do these calculations, like the times for you to pass the 0 degree or 360 degree, you need to correctly identify this time, and try to check the total angle that you have measured. You also need to make sure that the one that you calculated for the average angle is close to the one that you measured from the first direct measurement. The difference of these two values should not be very large. So this is the measurement of the angle with the repetition. It's one technique which you can apply to improve the accuracy of the angle measurement. And that's the first skill for the angle measurement. The next thing that I want to introduce is how to use the angle or the direction measurement to prolong a line. This is actually a very common implementation of the direction or the angle measurement. We want to identify extend a straight line on the road, or in the future we want to extend to create a curve on the road, which would be the lab 4 that you're gonna do in the experiment, in the lab experiment. So we will start with the simplest one, prolong line. So here we will have a straight line. Say that we have the line from A to B. From A to B is in a straight line, but we want to extend this line for a certain distance, and also make sure that the extended line is along the same direction of A to B. And with that, we will need to use we will need to utilize some help from the total stations or from the transit level to identify the directions of the line A to B. Say that if the A to B is only 100 meters, but we want to extend this one for like 10 kilometers, this would be in a very effective method based on the line of the sight and also the true angle that you measured. So this is just one simple implementation. Of course, if there's any object blocking your side of view, then that will be good. But if there are something in between, then we have to carefully think about it. Another thing that we need to think about is like for the extension of the line. Usually, if it's too long, say that is 100 meters between A to B. If it's 100 meters between A to B, but we want to extend this one for 10 kilometers, we need to set up some intermediate station. And because 10 kilometers is too long, and even if we have a small error for the angle direction measurement, it could be scaled up to a very large arrow. So the way for us to do that is like we will try to set up some intermediate stations, C, D, E, F, or more stations. What you're gonna do is like you're gonna just put the you put in the transient level at point B and have the backside to A, and then just keep the direction, keep the angle of the telescope, and get the foresight to point C. And then at point C, you do the similar thing. You have the backside to B and the foresight to D. But there will be some risk. Like if there's some error about the instrument, the angle that is set is supposed to be 180 degrees from A to B to B to C. It's supposed to be in a straight line. But if there are some errors in the instrument, then you may have found out in a very small error in the directions. But with more stations you applied between B and P, this kind of error will get larger and larger, and eventually the line that you identified, you assume to be the point in the straight line of A to B, is not actually in the straight line. In addition, you can find out the very large deviations between the one you estimated P prime and the true point you should identify. So this would be the potential error by just using the direct method. So we call this one as the direct method. A direct method to read the to find out the one point in the straight line by only using one measurement, one forward and one backward side. So in order to do that, what we propose, like we will introduce the double centering method. So yeah, with that, we will first have apply the direct method at point B. So we have the backside to A and the foresight to C, and of course assume that there might be some potential errors about the angle and direction measurement. So say that is with these errors, we find out the location as C prime. But what we do is like we will try to reverse the telescope and then apply another direct measurement, have the backside to A, have the foresight to C. As you already reversed the telescope, what you will find that with the foresight, this minor error in the angle or in the direction will go to upward direction, and with that you can find out another estimated location for C. That will be C prime, which will be about this C double prime, which will be about the C prime. And in the actual measurement, to identify the point of C, you just need to find out the midpoint of C prime and C double prime, and we're going to use this midpoint as C. This will try to help you to eliminate the impact from or eliminate the errors from the instrument. And you can repeat this process again to find out the midpoint to represent the point D, and then you can get some point E, F, until you eventually find out the point of the P with the designed distance. So that would be the two methods for us to prolong a line. One is using direct method, the other one is using the double centering method. And we claim that the direct method has some weakness when there are some instrument error or there are some human errors when you are measuring the direction or angle. So this is also the part you have to pay attention in your field experiment. So the next thing we have to consider is like if there's something between the when you are trying to extend the line, but if there are something in between to block your side of the view. Then we need to think about different methods to extend the line virtually and overpass these objects. So for example, if we have a line from A to B, which is given, and we want to extend the line to cross the building and find out another distance from G to H. This line GH should be along the same direction of A to B. So to do that, the first method we're going to do is trying to move the line AB parallelly upwards until you find out the region that you can have the clear view for the other side of the building. So we will have the make sure that this kind of parallel movement satisfy two conditions. First, the distance of C to D is the same to the distance of A to B, and also we want to make sure that the line A to C is perpendicular to the line A to B. Similarly, B to D is also perpendicular to A to B. So with that, it means that you move the line parallelly upward, and then you can do the regular operation to prolong a line from C to D to some distance and find out the segment E to F. And of course, you need to identify the value, the segment of EF. Make sure that the EF with the same distance of the target line G to H, and then you need to move this one downwards parallelly, and find out the value of the target line G to H. We have to make sure that E to G is perpendicular to EF, and also we have to make sure that the F to H is perpendicular to EF. In the meanwhile, there's one critical condition. We need to make sure that EG equal to FH equal to AC equal to BD. This is the critical condition for us to make sure that the EH and AB are assigned in the same direction. So that's one method for us to go through the extend the line through the object through the building. We have another method which can realize the similar objective. For example, we want to extend the line to cross another object. This is the part that we cannot see through. So we are given with the A to B, and we want to extend the line from D to E. So what we do is like instead of moving the line A to B parallelly upwards, we will just start from the point C, and draw the line from B to C with the angle alpha. And this point C should have a clear view of line A to B and the line D to E. And the next step is like we're gonna try to start at the point C and draw a line with the deflection angle of 2 alpha. While previously the angle is set as alpha, and at C you should have the deflection angle of 2 alpha, and draw the line along this direction. Make sure that B to C has the same distance from C to D, and then at the point D, you get another deflection angle, which would be deflection angle to the left, and then you can start with laying out the line along this direction, and that will be the line with the same direction of A to B. So here D to G and G to E will be along the same direction of A to B. So this is the way for us to draw a line or to extend a line passing through the obstacles or passing through some high buildings that you cannot have a very good view to the other side. So with that, I have finished the introduction about the fundamental angle measurement. Do you have any questions so far? You can raise your hand or leave your message, leave your questions in the meeting chat. Any questions? Okay, if there's no questions, I will go to the next. I'll go to the next one about the traverse surveying. So I got the questions about the direct method. So which part are you talking about? Are you talking about the this method? Okay. If I'm talking about this one, the one before this one, okay. So it's this method. It's this one that you are mentioning about. So basically these two will be the same. So basically, if you are trying to prolong a line, so say that you are assigned with a task given a line A to B, and you want to extend this line to like a 10 kilometers away, or say that 1 kilometers away, but your tape will only measure at every 100 meters. So what you're gonna do is like, first you put in the level transit here, or satellite, or total station here. What you're gonna do is like you will try to have on the backside to point A. With that, your telescope will directly face to point A, and then you have to lock your instrument and reverse the telescope. So the telescope will gonna be reversed. So which means that you will have the the changes of direction about 180 degree, or you can just rotate your scope about 180 degree, and with that, you can find out the ID. Theoretically, you should find out the line which will be along the same direction of A to B, and say that it's point C. And then you can measure another distance, say that 100 meters. You can measure another distance about 100 meters. And then once you identify point C, you do the similar process, find another distance of another point of D, and eventually can find out the point P. But this is for the theoretical situation. It assumes that your instrument is very great, it's very accurate, and your operation is perfect. If there's any minor errors, say that if there's any minor errors about the 180 degree that you are assumed supposed to adjust, but your instrument has certain errors, the 180 degrees not measured in the instrument is not 180 degree. Instead, it's 179 degree, 59 minutes, 50 seconds. There will be 10 seconds error. Then what you will observe is like you will see the instrument will give you a direction that is a little bit behind. It's not along the straight line, so you have this kind of 10 minutes error. And if you repeat this process again, you have another 10 minutes error. And say that for this case, for 100 kilometer extension, you will have 100 by 100 meters. So you need to do the repeat this measurement for 100 times. What you will get that eventually the error, the angle that you observe is 100 times 10 minutes, 10 seconds. So that is 1,000 seconds 1000 seconds equals to well, equals to let me see what's the what's the value should be. 1000 divided by 60. So that will be 60 minutes and 40 seconds error. This would be the error. So it could be in a very it could result in that case it would result in several meters difference about the true location you have to identify and the estimated value. So that's the reason we want to introduce the double-centered method. With double-centered method, you can try to minimize the error from the instrument error. Oh. Okay. Any other questions? If no, I will go to the next slides. You can also find out the slides on Emily to learn about the traverse. Traverse is actually a technology which will try to combine all the fundamental measurement together, the distance measurement, and also the leveling and the direction measurement. So the let me try to remove the timing for this one. Okay. So the usually for the traverse surveying, we have to consider it comes with several parties. The instrument operator, a head tapeman, and the rear tapeman. So we need to have the instrument to measure the angles, and also we need the two persons to identify the start and end point for the backside and the foresight. And in the traverse survey, we have to use usually we're going to use the theodolite, the total staging. We also need to use the steel tape or some electronic distance measurement devices. This will be similar to what we were doing for the lab 3. On the also we need to specify some stations or the hubs to where you can try to identify the distance that you need to measure, the site you have to measure, and or for the lab experiment you are trying to measure and close the polygon around the building, around the parking lot. This is one part of the traverse surveying. And generally there will be 3 types of the traverse surveying. The first one is called the open traverse. In the open traverse, we are provided with the initial line. So you are given with the direction of A to B, and then you will start from B to do the measurement about the to do the traverse surveying about some other lines from B to C, C to D, D to E, and you don't know the information of those lines. B, C, C, D, and the D. So this is called the open traverse surveying. The second one is called the closed traverse surveying. So this indicates that you are provided with the initial lines and the end lines. You know their directions. You know their angles, and you will need to use this information to measure the lines in between. Say that from B to C, C to D, D to E, E to F. So you know the information of A, B, and F, G, but you don't know the information of B, C, C, D, D, E, and E, F. So this is called the closed traverse. And the last one is the closed loop traverse. This is a little bit different from the closed traverse. In the closed loop traverse, still you just know the information of one site or one line, but you will do the surveying about multiple lines, and eventually you will return back to the point A. So you know the information of AB, but you don't know the information of BC, CD, DE, EF, FG, and GA. So you don't know the information of those sides. For those sides, you don't know. This is the things you have to measure. But we're gonna use the initial known information, the direction and the line, the distance of the line A to B, to try to find out the potential errors during your experiment. And this also applies for the closed traverse, but for the open traverse, there's no way for you to estimate the potential errors. So for the traverse surveying, we can actually conduct the traverse surveying with different type of the angles. The first one is called the deflection angle traverse. Of course, here we are talking about the closed traverse. So with that, we are given with the initial condition of the line S to R, and we also know the information of the last line M to N. But we don't know what happened. We want to use this information to measure the lines in between. So we have a set of lines. So this is a T, U, V, and for the deflection angle traverse, instead of using the interior angle or the angle to the right, we're going to introduce the deflection angle. So for the first one, we have the alpha 1 to the right, and for the second one at the point T, what direction it is? It's to the left or to the right? Do you have any ideas about it? Do you know what's the angle it is? What's the direction it is? Left or the right? So if we draw this one, you can clearly see the draw the deflection, you can clearly see the direction. So here, see that the angle is alpha 2, and if we stand at the point T, is the angle to the left, so it's alpha 2L, and similarly at the point U, we have alpha 3R. We have the at the point V, we have alpha 4R, and at the point M, we have alpha 5 left. So in the deflection angle surveying, traverse surveying, we are given the angles, the deflection angles at the actually the directions of the line, this the initial line SR. We know alpha 1, alpha 2, and alpha, in this case that will be alpha 5. We can actually try to use this information to calculate what's the azimuth of the line, M to N. So basically, if we are provided with the azimuth of the SR, then the estimated line, the azimuth of the M to N could be the azimuth of SR plus alpha 1 minus alpha 2 plus alpha 3 plus alpha 4 minus alpha 5. If we want to make it general, that will be the azimuth of the initial line plus all the deflection angle to the right minus all the deflection angle to the left. So this is the this is what applies to all situations. So this is for the deflection angle traverse. You have the estimated azimuth of the line M to N. Then you can find out the error. Well, that will be the estimated value minus the true value. And I'm going to use this one to do the correction. So this is for the deflection angle traverse. And here in the next step, I'm going to show you why we will have this equation, why we're going to use the why we're going to summarize add the angle to the left to the right, and why we subtract the angle to the left. So here, let's just consider the first lines, the line between the RT and TU, which would be the part, here. Say that we know the. Let's first draw the. Let's just first draw the line, assuming that. Assuming that you know the azimuth of RT. So this is R. This is R, this is T. And we want to find out the azimuth of T to U. So this is the deflection angle. Well, in this case, in the previous example, that will be alpha 2L to the left. So with that, we can find out the azimuth. In this graph? We can find out the azimuth of RT. The azimuth of RT should be identified from the North Pole. This is the North Pole. This is the azimuth of RT. And similarly, you can find out that this is also the azimuth of RT. And with that, you can find out the azimuth of TU. This would be the azimuth of the TU. So clearly, you can see that the azimuth of TU will be the azimuth of RT minus alpha 2. Here, alpha 2 is to the left. So we have this, we will subtract the value from the angle. So that's for the deflection angle to the left. And I see one question is about how to define the angle to the left or the angle to the right. So this is about the definitions of the deflection angle. So say that we have two lines A, B, and C. So we want to find out deflection angle at point B. From AB to BC, what you're going to do is like you're going to extend the line A to B. And you will stand at a point, suppose that you will stand at the point B, and you look at the extension. Well, if the line BC is on your right side, this would be the deflection angle to the right. But for the other case, A, B, and C, you stand at the point B, and you look at the extension. This is where you're going to look at, where you're going to see, and you will find that the line BC is on your left. So in this case, that will be the angle to the left. So this is the way for us to define the deflection angle. I hope this explains your questions. Okay. Do you have any additional questions? Okay. If no, then I will go to the next example to see why we should add the angle to the right for the azimuth. So let's go to see another thing in the example, in the previous example. So we have the line north direction. We have the line U to V, and then V to M. U to V and V to M. With that, we have the deflection angle to the right. So this is alpha 4 right, and we can then use the azimuth of u to v to find out the azimuth of v to r. So for the azimuth of u to v, you can find out this is azimuth of u to v. This is the north direction, and which is also the value between the north direction here and the extended line. So this is also a u to v. And the azimuth of v to m, from the definition, this is the azimuth of v to m. And if you, based on the definition, you can clearly see that the azimuth of v to m is the azimuth of u to v plus the deflection angle to the right. So that one gives you the ideas why we will add the deflection angle to the right and subtract the deflection angle to the left. So I think that will be the most important part for the deflection angle travel survey. And in the field experiment, you will try to you're going to observe the azimuth for the deflection angle traverse. You will try to observe or to measure the deflection angle. So you have the you have the initial directions of SR, and then you're going to measure the deflection angle. This is the angle to the right, and you also have the deflection angle at the point T, deflection angle at the point U that will be measured. So you have this value, and this value. Those values are all observed from the experiment. And also you have the true value. This is the true value from the which are provided. We know the information of the line from M to N. And this is the part we observed, or we collect from the field experiment. And the part on the right is the something we need to calculate. And I don't have enough time to show you how to calculate this one, so I will leave this one for the next lecture. In this lecture, in the next lecture, I'm going to show you how to calculate the azimuth of each line, as well as how we can find out the error and how we're going to do the correction about each line with the error we calculated to make sure that your estimation is correct for all the for all different lines. Okay. So with that, I will stop the introduction about the contents in this lecture. And before I leave the class, is there any questions about it? So okay, if we don't have any questions, that will be all for the lecture today. And also, I have uploaded the fourth homework assignment on Avenue to learn about the angle measurement. So you can start working on that. The deadline will be next week. Okay. Okay. I guess that will be all today. Thank you very much for your time, and just feel free to let me know if you have any additional questions. Okay. Okay, that will be all. Thank you very much, and I will see you next week.